Isaac Newton's work on the laws of motion, gravity, optics, and mathematics laid the foundation for much of the physical sciences. Against the advice of his mother, he entered Trinity College at Cambridge and 8 years later was appointed professor of mathematics. Of course, everybody who is interested in science knows about Newton's laws of motion, that Newton's three laws govern the motions of all objects. But not everyone knows that Newton was highly influenced by Lucretius. Newton wanted to use certain passages of Lucretius on the nature of things to prove that he understood the concept of inertia. Newton got ideas from Lucretius. He got ideas from Lucretius' belief in the indivisibility of atoms. For example, the word quantum occurs in the Principia Mathematica, where Newton seeks to specify and clarify what he means by inertia. Newton also made other references to Epicureanism. Isaac Newton was not the only one influenced by Lucretius. Gottfried Wilhelm von Leibniz was also influenced by Lucretius' writings. It is possible that both Newton and Leibniz were influenced by Lucretius' writings and got mathematical ideas from his writings. It is possible that Lucretius could have influenced the development of calculus. Lucretius still remains relevant to modern developments in mathematics because of his description of the atom and the universe. Newton's masterpiece, the Principia Mathematica, says that the quantity of any centripetal force may be considered as of three kinds: absolute, accelerative, and motive, but we skip to the accelerative centripetal force. I quote Newton. He says, because taking away or allowing for the resistance of the air, it equally accelerates all falling bodies, whether heavy or light, great or small. This quotation is a reinstatement of Galileo's experiments of balls rolling down inclines, which allowed him to firmly establish that the gravitational acceleration is the same for all objects. In the late 16th century, Galileo postulated that air resistance is the reason that objects with low density and high surface area fall more slowly in an atmosphere. He carefully hypothesized that the distance of all falling objects is proportional to the square of the time elapsed.